So in 12.1, what we're going to be looking at this time is, again, we're doing hypothesis testing. But if you remember in chapter 11, we were hypothesis testing either about a mean or a population proportion, where we were saying, well, we think the mean is this thing, but let's test whether it's actually different than, greater than, or less than what we thought it was. And that was based off of some sample data that we got. This time what we're doing is we are comparing two means to one another. So we're saying, okay, I have these two different populations and I want to compare their means. So I'm going to take a sample from each one of my populations. I'm going to look at some data for these samples and I'm going to compare that sample data. And based on what that tells me, it's going to tell me whether those population means are the same, different, greater than, or less than one another. Okay. So all we are doing now is just comparing two different population means. This is done in very much the same way. We're dealing with test statistics. We're going to link this to confidence intervals, and we're going to see how to do this on a calculator. The first thing that we are going to look at is when you know what the population standard deviations are for each one of the populations. So let's say you have this population here and another population here. Okay, we'll say that this is population 1 and this is population 2. Okay, population 1 is going to have mean mu1, population 2 is going to have mean mu2. And then out of each of those, we're going to take some sample. Okay, so this is going to be sample 1. And then we're going to take a sample out of this other population and we're going to call this sample 2. Okay, sample 1 is going to have mean x1 bar and sample 2 is going to have mean x2 bar. Okay, now first we're going to assume that we know our population standard deviations. Okay, so we're going to assume that we know what the standard deviations are for each one of our populations. So let's say that population 1 has standard deviation sigma 1 and population 2 has standard deviation sigma 2. Okay, now if you remember back to chapter 11, if we knew what the population standard deviations were, we used a z-test. If we didn't know the population standard deviations, it meant we had to use our sample standard deviations, which meant we had to use a t-test. But in this case, because we know our population standard deviations, we know that it is going to be some kind of z-test. Okay, so keep that in mind as we go through this. Why is all of this useful? The reason that we like to do this is comparing two populations to one another. It's done a lot in things like, let's say that you were a car rental company and you wanted to compare what the gas mileage was for two different models of car. Okay, you would like the gas mileage on a car to be pretty good, okay, because it's cheaper. Okay, so maybe you could be a car company and you just wanted to know which make or model had better gas mileage. So you're going to take each one of those models of car and you're going to look at the gas mileage for the whole population. Okay, and you want to compare them. Okay, so you want to compare the gas mileage on each one of these cars. That's where it's useful. Okay, any kind of comparison thing is where this becomes useful. Okay, so what we are looking at here is, remember before when we were dealing with looking at whether the population mean equaled this particular value or whether it was different than, less than, or greater than a particular value. In this case, what we want to know is, are our sample means close enough together that we can assume that our population means are equal? So what we want to look at is, are the sample means close enough together if they're close enough to one another, then we can probably assume that the populations from which they come from have the same mean. Okay, if you take samples out of two different populations, as long as you've taken a representative sample, if those sample means are close enough, it's probably a pretty good guess that the populations that which they come from have the same mean. Okay, so if the sample means are close enough to one another, it probably means that your population means are very close together, which means that you could assume that they're almost equal. Okay, so are the sample means close enough to one another that we can assume that the population means are equal? Okay, so if we want to see if our sample means are close enough together, okay, I want to look at the difference between my sample means. So this time, rather than looking at the distribution of a single sample mean where the sample comes from a single population, what I now want to do is look at the difference between two sample means and look at the distribution of the difference between the sample means. So if you remember before, when we had one population, we took one sample from that one population and then we took the distribution of the sample means, and that is what gave us that test statistic that we were using in our hypothesis tests. What we are doing now is that we need to look at the distribution of the difference between the sample means, because we want to see how they differ from one another. Are they close enough together or too far apart? So now, because of this, we need to look at the distribution of x1 bar minus x2 bar. So I'm looking at the distribution of the difference between the sample means. This is going to change your test statistic. Okay, it's going to be slightly different than it was before, obviously, because now you've got x1 bar and x2 bar. Okay, it's not immediately obvious what this is going to be. It's just going to have to be one of these things that you kind of remember the formula for or write it down and have it next to you. You shouldn't need to calculate this too much because your calculator will do this for you when I show you how to do the short way, but just be aware of it, okay? But most of the time you can use a calculator. So this time, okay, we'll talk through this. Your test statistic, if you were conducting a hypothesis test here, your test statistic is going to be Z is equal to, it's a pretty long formula, but we'll talk about it after we've written it down. Okay. So the setup of this test statistic should remind you very much of what we've had before, okay? Whenever we were looking at a test statistic before, we always had, let's say, like the sample mean was here, and then the population mean was here, and then the standard deviation was always here. So it was always the sample mean minus the population mean divided by that standard deviation of the sample means, which always involves something to do with the sample size. This is very much the same, okay? We've got the difference in the sample means minus the difference in the population means, and then this term on the denominator is actually the standard deviation of the difference in the sample means. So it does look different this time because we've got two different sample means, two different population means, but it is very much the same setup. Okay, so keep this test statistic in mind as you go through this. Okay, as I said, your calculator will do it for you when you conduct one of these tests, but make sure that you know where it comes from, and it's a very similar setup to what we've had before. So when do we use this test statistic? We use this test statistic when we do these hypothesis tests. And when we conduct a hypothesis test, what we're actually testing is whether the population means are the same or whether they are different, less than, or greater than one another. Okay, so basically we want to see if they're equal or not. So first thing we have to do is to write down our null and alternative hypotheses. Well, our null hypothesis is always equality, okay? So we're going to assume that our two means are equal to one another. So whenever you do a hypothesis test, when you're doing this about two means, okay, your null hypothesis is always that mu1 would equal mu2, that the two population means are equal. Another way to write mu1 is equal to mu2 is to write mu1 minus mu2 is 0. Okay, that assumes that those two are equal. Your alternative hypothesis can have three different forms, okay, as always. You can have that mu1 minus mu2 doesn't equal 0. That's a two-sided hypothesis. You can have that they're greater than 0 or less than 0, okay? Now, bear in mind what each one of these means, okay? If mu1 minus mu2 doesn't equal 0, it just means that mu1 doesn't equal mu2. It just shows that they are different. So whenever you get a problem and it says, conduct this hypothesis to see whether the means are different, that's when you use do not equal, okay? For greater than, if I put a greater than 0 in there, if you rearrange that formula, that would be that mu1 is greater than mu2. Okay, so that shows that the first population mean is greater than the second one. When mu1 minus mu2 is less than 0, that's the same thing as saying mu1 is less than mu2. So the first population mean is less than the second population mean. So it depends what the question is asking. But keep that in mind and make sure that you have these means the correct way around depending on what the problem is asking. Okay? So that is your null and alternative hypothesis. So when you get a problem like this and you need to conduct a hypothesis test where you are comparing the two means, what you're going to do is a two-sample z-test. We're going to do a two-sample z-test here because we know in this particular chapter what our population standard deviations are. So we know the standard deviation of population 1, we know the standard deviation of population 2. Later on, when we do a two-sample t-test, that is when we know the standard deviation of each of our samples that come from the populations, but not necessarily the standard deviations of the populations themselves. So in this case, we know our population standard deviation for both population 1 and population 2. So it's what we call a two-sample z-test. Z, again, because we know those population standard deviations, and it's a two-sample test because we have two samples, one coming from each of our two populations. So if you go to stat and go across to tests, you should see option 3 is a two-sample z-test. Okay, as I said, later on we're going to do a two-sample t-test. But right now, everything that you're going to be doing is on a two-sample z-test in this situation. You are going to be inputting statistics. It's going to ask you for the population standard deviation of each of your populations. So that's sigma 1 and sigma 2. Then x1 bar is the sample mean for the first sample. n1 is the size of the first sample. x2 bar is going to be the mean of the second sample, and n2 is the size of that sample. And then you pick whether you have a difference, a less than, or a greater than. So you are going to have to adjust your alternative hypothesis in order for it to match this. Okay, remember, we always have mu1 minus mu2 is either not equal to, greater than, or less than 0. What this tells us is how mu1 relates to mu2. So you have to make sure that you get your populations the correct way around, so you know whether you are looking at whether the first population mean should be less than the second population mean, or whether the first population mean should be greater than the second population mean, or as in the example that we're going to look at in a second, it is a does not equal to 0, so it means that mu1 does not equal mu2. So you may have to adjust the formula on the alternative hypothesis, but it should always be, if you have a does not equal, it's that one. If you've got a less than, it's that one, and a greater than, it's that one. Just make sure you have your populations the right way around, so you are comparing the correct means, so you know which one is greater than the other one or which one is less than the other one. We are now going to do an example actually with the data that I have in the calculator right now. And it's this example here. And it says that a medical researcher wants to compare the pulse rates of smokers and non-smokers. He believes that the pulse rate for smokers and non-smokers is different and wants to test this claim at the 0.1 level. Okay, so we know that we've got a difference here. We are looking at mu1 minus mu2 does not equal 0. Okay, then it says that we've got a sample of 60 smokers. Okay, so our first population is the smokers, and they have a mean pulse rate of 84. So my sample mean for those 60 smokers is 84. And then we took 49 non-smokers. They're going to be my second my second sample is my non-smokers, and I've got 49 in my sample of them, and they have a mean pulse rate. The sample mean there is 82. Then we've got our two population standard deviations. So we know that the standard deviation for the population of smokers is 10, and the standard deviation for the population of non-smokers is 6. So it should tell you which one is mu1 and which one is mu2, so that you get them the right way around. So as I said, in this example, they're taking mu1 to be the mean for the smokers. So we know that population 1 is the smokers and population 2 is the non-smokers. So make sure you get them the right way around. In this case, you're okay because it's just a difference between the two. But if it said that they wanted to know if one was greater than the other, you have to make sure you have them the right way around. Otherwise, your hypothesis test is going to be incorrect. So make sure you get your populations the right way around, and we're going to put this into our calculator. So let's come back to here. So from this, I have my standard deviation of the smokers, standard deviation of the non-smokers. I've got x1 bar, that was my sample mean for the smokers was 84, and there was 60 smokers that I had in my sample. Then for the non-smokers, their mean was 82, and there was 49 in that sample. In this problem, we had a difference. We wanted to see if mu1 minus mu2 was different than 0. If you alter that and change that around, that means mu1 does not equal mu2. And then you're going to go down here and you're going to calculate. And this is what we get, okay? So top line should correspond to your alternative hypothesis. So we said that mu1 minus mu2 should not equal 0 because we had a difference problem. So that means mu1 does not equal mu2. Then this z value here is my test statistic. So this is exactly like when we had test statistics previously, where you could compare it to a critical value if you wanted to. And that long formula that we just looked at in this case, and what that test statistic formula was, they've done all of that for you. So in this case, the test statistic is about 1.29. The p-value, okay, remember that is the probability of having a test statistic that is that far away from the mean, okay? So this means that p is roughly 0.2-ish, okay, it's 0.1968. So what I can then do, we said that alpha, my significance level, was 0.1, okay? So I can compare my significance level and the p-value and see whether I'm going to reject or fail to reject. In this case, p is greater than my 0.1 level of significance, so therefore I'm going to fail to reject my null hypothesis. Remember, p has to be less than alpha in order for us to reject in favour of the alternative hypothesis, but in this case, p is greater than alpha, so we're going to fail to reject our null hypothesis. So that means that we are taking our null hypothesis as given, okay? We think that our null hypothesis is correct. That means that we think mu1 minus mu2 does equal 0, meaning that mu1 equals mu2. We think that from the sample data that we have, that our population means should actually be the same, and there is nothing to contradict that, okay? So from the sample data given, we can see that the sample means are close enough that we can assume that our population means are equal. So this is the problem fully written out with all of the values, and again, because we are failing to reject our null hypothesis, we are assuming that mu1 minus mu2 does equal 0, and that means that mu1 must equal mu2. Okay, I would actually highly suggest that you go ahead and when you do any of these problems, before you plug anything into your calculator, please actually write the values down and write down what each value is. So you tell me what each of the standard deviations are, what each of those sample means are, and what each of the sample sizes are, and make sure that you get your means the right way around, especially when you have a one-sided hypothesis with either a greater than or a less than. Please make sure you get them the right way around, and it will tell you that in the problem. Now, another way that we could have conducted this problem, and this problem in particular, is by using confidence intervals, okay? You only were able to use confidence intervals if you look back in 11.3. We could only use confidence intervals in hypothesis testing when we had a two-sided hypothesis. So when we've got that two-sided alternative hypothesis that does not equals, okay, that means that we can go ahead and use a confidence interval instead of using one of these two sample z-tests, okay? This time it is slightly different. If you remember, when we conducted a confidence interval in 11.3 in order to do one of these hypothesis tests, what you did was you went ahead, found the confidence interval, and then you saw if the population mean that value that you thought that value was, you saw if it was inside that interval. If it was, then you failed to reject the null hypothesis. If it wasn't, then you rejected the null hypothesis, okay? So go back and look at 11.3 when we did that. So when we did that, okay, again back in 11.3, you had something, your null and alternative hypothesis looks something like this, okay? So you had a two-sided alternative hypothesis. Your null hypothesis said, we think that the mean is equal to this mu0 value. Okay, 3, 4, 5, 6, it doesn't matter what the value was, okay? And then the alternative hypothesis was, we were hypothesizing that the mean did not equal that value. You went ahead, given the sample data, you conducted the confidence interval, and then you saw whether this value was actually inside that confidence interval. If that value was inside the confidence interval, we failed to reject our null hypothesis. Okay, we said, well, that means that our mean is close enough to our sample mean, therefore we're going to fail to reject the null hypothesis. But if that value fell outside of that range, it meant that our population mean was far enough away from our sample mean that we could no longer accept that null hypothesis. We had to reject that null hypothesis in favour of the alternative and say that the mean was not equal to that value. Okay, so we always looked at whether this value was inside the confidence interval or not. If we now relate this to the problem that we have, okay, our null hypothesis is that mu1 minus mu2 is equal to 0. Okay, that means that mu1 is equal to mu2. Our alternative hypothesis, again, we can only do two-sided alternative hypotheses if we want to do a confidence interval. Okay, you cannot do a confidence interval if you have a one-sided, if you have a greater than or less than. Our alternative hypothesis was that it does not equal 0. So this time what I'm going to do is, given the sample data, I'm going to conduct this confidence interval, okay, and I'll go through what the confidence interval is in a minute. You're going to find a confidence interval, and this time what you're looking for is whether 0 falls in that confidence interval. If 0 does fall in that confidence interval, it means that mu1 and mu2 are close enough together that we can consider them equal. If 0 does not fall in that interval, then we have to say that it's different to 0. We have to say that mu1 does not equal mu2. Okay, so this time what we're going to be doing is conducting this confidence interval and then seeing whether 0 lies in it. Okay, so our confidence interval this time, again, if you have a two-sided alternative hypothesis, our confidence interval is going to be x1 bar minus x2 bar plus or minus z of alpha over 2 multiplied by the standard deviation of the difference in the sample means, which we said was this thing here. It was the denominator of that fraction when we did the test statistic. Okay. This z value here, okay, that was the critical value. Okay. So whenever we did like test statistics and critical values and that stuff, that is the critical value. Okay. So you can go ahead and figure out x1 bar minus x2 bar minus this value. That will give you your lower bound for the confidence interval, and x1 bar minus x2 bar plus that term is going to give you the upper bound of our confidence interval. Okay, that's a lot of work to do. We don't want to be doing all of that. Okay, for a start, this term is horrible, but also we have to then compute what the critical value is. So there is a much easier way of doing this again on your calculator. So if you go to stat and go across to tests, again, we know what sigma 1 and sigma 2 are. We have our population standard deviations. So we can go ahead and use a two-sample z interval. Okay, it's a z interval, not a t interval. Okay, so a two-sample z interval. Okay, in my calculator, let me check what number it is. It's option 9 on that list. You're inputting statistics again, okay? And you're going to go down and input all of the values and all the data, okay? So it's, if we went back, we can do this for the example that we have, okay? Let me, oh, it was this slide here, okay. If we went ahead and did that same example, but this time, because we've got a two-sided alternative hypothesis here, so let's conduct a confidence interval, see what our confidence interval is, and then we can see whether 0 lies in that confidence interval, and we can see if we get the exact same decision at the end. So now I'm going to conduct that two-sample z interval, okay? Again, two sample because we are dealing with two populations, one sample from each, and it's going to be a z interval because we know those population standard deviations for each of my populations, okay? And this time we want to find the interval, and then we're going to see if 0 lies within that interval. So you're going to go to stat, go across to tests, and if you scroll all the way down here, you should find that number 9 is a two-sample z interval. We're going to do the two-sample t interval later when we know our sample standard deviations as opposed to our population standard deviations. So I'm going to click on number 9 and I'm going to input statistics. Okay, now I'm going to do this for the last example that we had. So remember, our population standard deviations were 10 and 6. Then x1 bar, that was our sample mean for the smokers. N1 was the sample size, we had 60 smokers. X2 bar was the mean of the non-smokers, and N2 was the number of non-smokers in our sample. Now remember, when you have a when you have a hypothesis test, and we're using confidence intervals in relation to the hypothesis test, whatever significance level they give you, so in this case it was 0.1, if you look back, alpha was 0.1, it means that the confidence level for that test would be 0.9, okay? So it's always 1 minus whatever the level of significance was for the hypothesis test. Okay, so we had a 0.1 level of significance, which means our confidence level is 0.9. So we're 90% confident that this particular interval should contain 0. So then I'm going to go ahead and calculate. And I get my interval up the top here. So my interval is going to be negative 0.5489 to 4.5489. What I want to see is if 0 falls in this confidence interval, okay? Looking back at our formula, if 0 falls in that interval, that means that these two things, x1 bar and x2 bar, are close enough together that I can consider the population means to be equal, okay? If 0 falls in this interval, it means these two things are close enough together, okay? Because this thing's going to be really, really small, okay, in that case. If 0 falls in the interval, these two things are close enough together that I can consider this thing to be true. mu1 minus mu2 is equal to 0, because if they're close enough together, I can consider these population means to be equal, if my sample means are close enough together, okay? So 0 does fall in this interval. That means that I can fail to reject my null hypothesis. So if 0 falls in the interval, it means the sample means are close enough together that we can consider the population means to be equal. Okay, so that means we fail to reject the null hypothesis. Okay, so in our case here, 0 falls in that interval. That means we fail to reject the null hypothesis, which means that we can consider the mean pulse rates of smokers and non-smokers to be equal. Exactly what we have said here. Okay, so when you have a two-sided alternative hypothesis, you can go ahead and either conduct this test and you can compare P and alpha as normal, or you can go ahead and do one of these confidence intervals. Okay, if 0 falls in that confidence interval, it means your sample means are close enough together that you can consider the population means to be equal, and therefore you're going to fail to reject the null hypothesis if 0 falls in this interval. If 0 falls outside the interval, it means your sample means are far enough apart that you can no longer consider your population means to be equal, and therefore you're going to reject the null hypothesis if 0 falls outside of that range. Okay. Okay, so now we want to look at 12.1b, which looks at the situation where you don't know the population standard deviations. So in 12.1a, you always knew what the population standard deviations were for both populations. That was given in the problem. But now we're assuming that we don't know those population standard deviations. This is more like real life, okay? You're trying to investigate something about the population means because you're not sure about what they are. You only know what the sample means are from each sample that was taken from each population. So if you don't know the sample means, you're not going to know what the spread of the data is. You're not going to know what that population standard deviation is. So this is much more like real life. So what we want to do is see how we conduct a hypothesis test where we're comparing the two means again. So we're still dealing with a case where your null hypothesis is mu1 minus mu2 is equal to 0. So we're assuming that mu1 is equal to mu2. Those population means are equal. And then we've got our alternative hypothesis, which can be one of three things. It can either be does not equal, less than, or greater than 0. Okay? But now, when we get given all of this information, they're not going to tell us those standard deviations of each population. Instead, they're going to give us the standard deviations of the samples that were pulled from each population. Now, because we don't know what the population standard deviations are, when you conduct a hypothesis test, in some way you still need to have an idea about what the spread of each of the population data are. Okay, so you need to roughly know how the data in each population is spread out. Okay, because you may have one that is like really spread out and one that is all kind of bunched together. Okay, and that's going to change what happens with your population means. So there is two ways of doing this. The first way is where you don't know what the population means are, but you are assuming that they are equal, okay? So in the first case, if you don't know what sigma 1 and sigma 2 are, you could assume that they were equal. Okay? This is the first case, so this is case 1. You can assume that they are equal to one another. So you know nothing about their actual value at the moment, but you can assume that they are equal to one another. What that does for you is it assumes that the data in each of the populations is spread out in exactly the same way in both of the populations. Okay, so they have an equal spread of data. What they actually do when they do this is they take the sample standard deviations, they square them to find the sample variances, and they average those sample variances out to find this population variance, kind of like an average, this average population variance that they're going to use for both of them. So when you assume that they are equal, the way that they do this is by finding the sample variances so you know that you are given the sample standard deviation for each one of the two samples. You have their sample standard deviation. So if you square each one of those, you're going to get the sample variance for each sample. And what you're then going to do is average them. Okay, so you're taking the average of the two sample variances. That will give you this population variance that is going to be used for both of sigma 1 and sigma 2. So what they're doing here, that's basically sigma 1 squared and sigma 2 squared, okay? So they're taking this population variance, okay, which is the average of the two sample variances, and they're going to use that population variance for both of the populations. Then all they do is you can square root both of those and you'll get sigma 1 and sigma 2, both of those population standard deviations. Okay, so what you are assuming when you do this is you're just averaging out the sample variances, okay, to give you this population variance that is then used and square rooted to find this population standard deviation that is used for both of them, and it's just an average of what we have from our sample. When you do this, what you are actually doing is pooling. That's what it's called. You're pooling the sample variances. Okay. When we actually conduct a hypothesis test in this manner, okay, you don't know what the population standard deviations are, okay? Bringing it back to what we did in chapter 11, okay, if you did not know what the population standard deviation was and you were conducting a hypothesis test, you only knew the sample standard deviation. So you had to go ahead and use a t-test, okay? If you did not know the population standard deviation, you used a t-test. And that is exactly what we do here, okay? In either one of these two cases I'm going to show you, you're going to use a two-sample t-test, okay? So in 12.1a, you had two populations. You took a sample from each one, but you were given the population standard deviations, and you were comparing the population means, okay? So we knew that we had two samples, and we were dealing with a z-test because we knew the population standard deviations. Here, we've got two samples from the two populations, but this time we don't know the population standard deviations. So we are using a two-sample t-test, okay, in either one of the two cases I'm going to show you.
When you pull up a 2-sample t-test on your calculator, it's found in exactly the same way. You go to stat, tests, and then go down, and option 4 on my calculator is a 2-sample t-test. Okay, you're inputting statistics, and it will ask you for all the same stuff that you did with the 2-sample z-test. It's just that now they are going to ask you for the sample standard deviations, SX1 and SX2, as opposed to the population standard deviations that we had before. Okay, so they're just going to give you that sample data this time. And at the bottom, you'll notice it will ask if something is pooled. Okay, if in the problem, and they will state it in the problem, if they state that they want you to assume that the population standard deviations are equal, you're pooling those sample variances in order to find that. Okay, so if they say that you're going to assume that sigma 1 and sigma 2 are equal, so if you are assuming that they are equal, sigma 1 and sigma 2, then you are pooling. So the answer to that is yes. The other case is case 2, where you're assuming that sigma 1 and sigma 2 are not equal. Okay, you're assuming that they're not equal. So if sigma 1 and sigma 2 are not equal, the question is, how do we find like a value for them or whatever? Well, the only way that you can do that is by using the sample standard deviations to estimate each one. Okay, so if you don't know what sigma 1 and sigma 2 are, and you are not assuming that they are equal, you're just going to estimate each one using the sample standard deviations. Okay, and then when you run a 2-sample t-test in this case, you would say the sample variances are not pooled. Okay, because all you're doing to find the standard deviation of each one is just finding the sample standard deviation that's given in the problem and using that as an estimate for each of the population standard deviations. You're not taking an average of the variances and then square rooting that to find the population standard deviation, okay? So in this case, when they are not equal, okay, you are not pooling those sample variances or the sample standard deviations. So therefore you're saying they're not pooled, they're not equal. So you are just going to estimate each one from the sample data, from those sample standard deviations. Okay. When you do these type of problems, okay, in both cases, the test statistic is very much the same. There's one slight difference, okay? In this case that you have here, so for case 1, okay, again, the calculator will find this test statistic for you. You do not have to do this by hand. For case 1, your test statistic, it looks very similar to what we did in 12.1a. It's going to look like this. What this is, okay, it's very much the same as what we had in 12.1a, as I said. You've got the difference in the sample means minus the difference in the population means, okay, which this is actually just going to be 0 when you plug it in, because you're assuming, if you remember, that value is always taken from your null hypothesis, so you're actually assuming that that's 0, okay? And then you're dividing that by the square root of this thing, and that is just the standard deviation of the difference in the sample means, okay? Now, you've got this SP squared value in here. If you remember from 12.1a, you had sigma 1 squared and sigma 2 squared in there. What that would be the variance for population 1 and population 2. So if you go back and look at what that formula was for the test statistic, okay, all it was the variance for each one of the populations. But here, we're assuming that those variances for case 1 we're assuming that those variances are equal. You're assuming sigma 1 squared is equal to sigma 2 squared. And the way that we did that was by finding the sample standard deviations, squaring them to find the sample variances, and taking their average. And that was the new population variance. That is what this SP squared value is, okay? It's the average of the two sample variances, and they've used that as the estimate for each one, okay? So that's all that SP squared value is. It's just the average of the two sample variances, okay? As I said, your calculator is going to do all of this for you, so don't panic when you see this. It's just what this test statistic would look like. For case 2, this is going to look very much the same. The only difference is this value here is going to become the variance for the first sample, and this value here is going to become the variance for the second sample. Okay, remember the variance is just the standard deviation squared. Okay, and we're going to estimate each one of those population variances and each one of the population standard deviations by what the sample data gave us. So a population standard deviation is estimated by the sample standard deviation. Therefore, the population variance is going to be estimated by the sample variance. So each one of those, and now we're not assuming that they're equal, we are just taking them from the sample data, like we set up here. So if you go ahead and look back at what we did in 12.1a, we're just assuming that each one of those sigma 1 squared and sigma 2 squared values is now equal to S1 squared and S2 squared, those sample variances instead. That is the only difference. So I'm going to go ahead and do an example of this in a second, but what I want to look at quickly is exactly the same as what we did last time again, okay? If you have a two-sided alternative hypothesis, okay? So if you have a hypothesis for your alternative hypothesis that has that does not equals in it, you can also conduct a hypothesis test for that using a confidence interval. But in this case, we're going to have to deal with a two-sample T interval, okay? If you remember in the last 12.1a, we dealt with a two-sample Z interval. In this case, because you don't know what those population standard deviations are, you've only got the sample data, it's going to be a two-sample T interval, which in my calculator, if you scroll all the way down, it's option 0, okay? This only works if you are dealing with a two-sided alternative, okay? If you look at my notes, I actually have what the T interval looks like. It's a very horrible formula. But again, all that T interval is looking at is it's looking at the difference in the sample means plus or minus some value. Okay? I will actually write it out just so that you have it. This is what the confidence interval looks like. Make sure should be -2 and then square root. I'm going to do this for assuming that we have pulled those sample variances. So let's say that this is your interval, okay? This is your confidence interval, okay? You've got the difference in the sample means plus or minus some T value, okay, this is all one value, it's just some T value, times that standard deviation of the difference in the sample means, okay? Again, don't worry too much about this formula, but this is what your calculator is looking at, okay? It's very much the same as what we did in 12.1a. It's just that now we're looking at this T interval as opposed to a Z interval. When you do this, okay, what you are looking at is how close together x1 bar and x2 bar are, okay? When you do this, as we did in 12.1a, you are looking at whether 0 lies in this interval, okay? Because you've got the difference in the sample means plus or minus this small value, okay? This whole thing's going to end up being a pretty small value in most cases. So if 0 lands in there, what it means is the sample means x1 bar and x2 bar, so the means of each of the samples, are close enough together that we can therefore assume that the population means are equal. Okay, so if 0 lies in that interval, it means that x1 bar, the sample mean, actually I should write it as x1, and x2 are close enough together that we can assume that mu1 is equal to mu2, which means that mu1 minus mu2 is equal to 0, which means we fail to reject the null hypothesis. Okay, so if you calculate this 2 sample t interval, okay, if you do not know what those population standard deviations are, you only know the sample standard deviations, you go ahead and do a 2 sample t interval, okay? You go ahead and do that. As I said, on my calculator, it's option 0. Again, they will ask you for whether you are pooling those variances, okay? So you're going to type in your sample standard deviations, but what it wants to know is what to use for these 2 values up here, okay? It's either going to use the sample standard deviations to estimate what those ones are going to be, or it's going to use this pooling technique where it takes an average. Okay, so you have to tell it whether to pool it or not, and it will tell you that in the problem. So please read the problem carefully. Okay, but if you go ahead and figure out what this interval is, it's on a 2 sample t interval. Again, only works for a 2-sided alternative. Okay, for a 2 sample t interval, if 0 is in there, you're going to fail to reject the null hypothesis. You could assume that those population means are equal. If 0 is outside of that interval, it means that the sample means are just too far apart, that therefore you cannot assume that the populations from which they come from have the same mean. So in that case, you're going to reject the null hypothesis if it falls outside. Okay, so that's 2 ways of conducting this hypothesis, depending on whether you want those population means to, the population standard deviations to be equal or not. Okay, but it will tell you that in the problem. But it's all conducted either by just doing a 2 sample t test or by doing a 2 sample t interval. If you have a 2-sided alternative, you can do that 2 sample t interval. It's up to you. Just as a heads up, when you do this, either you pool the variances or you don't, and that determines what your samples, what your population standard deviations are going to be, and therefore what your population variances are going to be. When you do that, if you do not pool them, so you assume that they're different and you're just assuming that one population standard deviation is equal to that sample standard deviation, and same with the other population standard deviation, it's going to equal the sample standard deviation for that other sample. If you do assume that that is the case, you are actually taking a more conservative approach. Okay? In terms of intervals, you would actually end up with a wider interval if you don't pool the variances as opposed to when you do, okay? But it would always tell you in the problem as to whether you need to pool them or not, but you would always end up with a wider interval if you don't pool them than when you do. So this is the first problem we're going to look at, and this is actually going to be a one-sided test. So let's look at this one, and we know for a one-sided test that we will have to use a 2 sample t-test. We can't go ahead and try to find the interval for it because the only interval tests that we can use are for when it's 2-sided. So because it's a one-sided test, we know we're going to have to use a 2 sample test. In this case, they're going to give us the sample standard deviations, so it's a 2 sample t-test. So let's read what it says. So the study was designed to compare the attitudes of 2 groups of nursing students towards computers. Group 1 had previously taken a statistical methods course that involved significant computer interaction.
Group 2 had a statistic methods course that did not use computers, so Group 1 used the computers and Group 2 did not. The students' attitudes were measured by administering the computer anxiety rating scale. A random sample of 15 nursing students from Group 1, so we know that the first group, okay, the first population, we've taken a sample of 15 of them, and they had a mean of 64.1 and a standard deviation of 7.6. Then from the second population, those that did not use the computer, they took a sample of 8 of them, and they had a mean of 71.1 and a standard deviation of 4.9. And the question is, can we conclude that the score for Group 1 is significantly lower than the mean score for Group 2? So we want to know, is the population mean for Group 1 significantly lower than the population mean for Group 2? And we're going to test this at the 0.01 level. So what I want you to do is to go to your calculator, and I'm going to go to Stat and across to Tests. Okay, and we're going to go and do a 2-sample t-test here. So let's go down to a 2-sample t-test. And we're going to plug in all of that information. I've already done that here. So I've got that the mean of the first sample was 64.1 with its standard deviation. Then I've got the first sample size was 15. Then the mean of the second sample was 71.1 with a standard deviation of 4.9, and that sample size was 8. And then we wanted to test, it was one-sided, whether the mean of the first population is significantly less than the mean of the second population. Then it comes to the thing where it asks if it is pooled, okay? That's whether we're going to pool the variances in order to find that population variance, okay? Now, in this case, let me go back to the problem. We can actually see on that last sentence it says, assume that the population variances are equal. Therefore, we are pooling the sample variances in order to give us this population variance. Okay, we're taking the average of the sample variances. That's what's going to give us this population variance, and they're going to be equal. So the variance of each population is the same. So therefore, the answer to this is yes, we are pooling the variances. So you're going to put yes on pooled. And once you've done that, you're going to go down and you are going to calculate. Okay. Top line should be what your hypothesis is, okay? This is the same thing as saying mu1 minus mu2 is less than 0 if we put it all on one side. So that would tell us that mu1 minus mu2 is less than 0, telling us obviously that mu1 is less than mu2. Then the second line, this t value is your test statistic, okay? In this case, the test statistic t depends on, as you saw when I wrote it down in the formula, it's going to depend both on that level of significance and it's going to depend on the degrees of freedom. In this case, the degrees of freedom when you are dealing with 2 populations and hence 2 samples, and you are looking for the t value, it's going to be the 2 sample sizes added together minus 2. So you'll see if we come to here, the degrees of freedom is 21, okay? Because our first sample size was 15, our second sample size was 8, we add them together and subtract 2, and that gives us 21. When we were just dealing with one population and one sample and did a t-test, then the degrees of freedom was just that sample size for that one population minus 1, okay? But when you are dealing with 2 populations and hence 2 samples, then it's going to be add them together minus 2 for the degrees of freedom. Then this line here, p, okay, that is your p-value. That is what you are going to compare to your level of significance to see whether we're going to reject or fail to reject. In this case, p is greater than alpha. Alpha was 0.01. P is greater than alpha, only just, but it is greater. So in this case, we're going to fail to reject our null hypothesis as p is greater than alpha. We reject when p is less than alpha, and we fail to reject when p is greater than alpha. So that's how we can do this 2-sided hypothesis test. So this actually tells me, because we are failing to reject the null hypothesis, that means that we are considering
mu1 minus mu2 equals 0, which tells me that mu1 equals mu2, okay? My null hypothesis is stating that those two means, those two population means are actually equal, and we are failing to reject that in this case, so we are assuming that whether these nurses use computers or not doesn't make any difference. Their scores are actually going to be the same across the population.